Hello, everyone, and welcome to the lecture series on complex analysis. Today, we will start with the derivation of the sufficient condition for the existence of derivative of the function, a complex valued function f of z, in polar coordinates. This, in the exam point of view, uh, this question may appear like this: drive the CR equations in polar form, or state and prove the sufficient condition for the derivative of f of z to exist in polar coordinates. And thirdly, it may appear as drive f prime of z in polar form. So, the things that are coming in these slides will answer all of the questions. So, let's start proving the theorem, the sufficient condition for the existence of derivative of f in polar coordinates. So the theorem states like this, and this is the rephrasing of the theorem that we have proved for the Cartesian coordinates and the Cartesian form of CR equations. Just the rephrasing is in the polar coordinates r and theta. So let the function f of z, which is equal to u r theta plus iota v r theta, be defined throughout some epsilon neighborhood of a non-zero point z naught, where z naught is now expressed as r naught exponent of iota theta naught in r theta form, whereas before z was expressed as x plus iota y. Suppose that the first order partial derivatives of the functions u and v with respect to r and theta exist everywhere in the neighborhood. Those partial derivatives are continuous at r naught theta naught and satisfy the polar form this of the Cauchy-Riemann equations at this point. Then, if all these conditions are being satisfied by f, then we say that the derivative of f at z naught exists and its value being this. We'll proceed towards proving this theorem by showing that the CR equations in polar form are exactly an alternative form of the CR equations in Cartesian form. When we establish this thing, we can, from that theorem for the Cartesian coordinates, from that sufficient condition, we can restate this theorem that the conditions that hold for those coordinates are also valid for the polar coordinates, and so on. All the other conditions are valid, and the derivative exists for polar form too, and its value being this, and this value can be evaluated by some algebraic manipulations. So let's start with the proof. We already know the sufficient condition for the existence of derivative of f of z when z is x plus iota y. Now we will restate the same theorem in polar form. We will restate the theorem in polar form using the coordinate transformations x equal to r cos theta and y is equal to r sin theta. Using this coordinate transformation, the function that was before in x and y coordinates will turn to r and theta coordinates. Suppose that the first order partial derivatives of u and v with respect to x and y exist everywhere in some neighborhood of a given non-zero point z naught and are continuous at z naught. We are supposing that ux, uy, and vx, vy exist everywhere in some neighborhood of z naught, and these partial derivatives are also continuous at z naught. Then, according to this condition, um, the corresponding partial derivatives exist with respect to r and theta and also are continuous. And we can apply the chain rule for differentiation of real valued functions of two real variables to express these partial derivatives with respect to r and theta in terms of the previous ones. So, what's the explanation of this point that why these conditions also similarly hold in for um, r and theta coordinates? So, we have written this explanation in the next step, that is this. Since we are using the coordinate transformation x equal to r cos theta and y equal to r sin theta, so u r theta can now be expressed in form of this as a composition of such functions, and v r theta can be expressed as vx r theta y r theta, where x and theta are now the functions of r and theta because x equal to r cos theta and y equal to r sin theta. From these transformations, you can check that um, since cos theta, sin theta are trigonometric functions and they are smooth functions. And what we meant by smooth functions are known to be infinitely differentiable functions. Since trigonometric functions are infinitely differentiable functions, so x and y both are smooth functions, that is infinitely differentiable. And as before, we know that there also the derivatives of x and y with respect to r and theta are also continuous. Okay, the partial derivatives, and we already know that u and v have continuous first order partial derivatives in x and y. So, since u and v have continuous partial derivatives with respect to x and y, and x and y are smooth functions, and they also have continuous partial derivatives with respect to x and y, with respect to r and theta. So, the composition of u and v with smooth functions x r theta, y r theta, the composition of two smooth functions is also a smooth function. So by this we can see that u and v with coordinates r and theta are also uh, the first order partial derivatives actually are continuous because of the smoothness of their um, components u and x. So this was the reasoning that was being used there. Now we just rewrite the partial derivatives in form of this: ur is equal to ux cos theta plus uy sin theta, and u theta is equal to minus ux r sin theta plus uy r cos theta. Likewise, vr and v theta can be written as this. Since we are supposing that all the conditions for the existence of f prime of z holds in case of Cartesian coordinates, we are supposing that thing. So, since it is involved in those suppositions that the partial derivatives um, of u and v with respect to x and y also satisfy the CR equations. So these are the CR equations in Cartesian coordinates. We can use these CR equations in these equations and we get this. Now equation 3 are um, VR is equal to Vx is equal to minus Uy, Vy is equal to Ux, and here minus Vx is equal to Uy and Vy is equal to Ux. All these V's are replaced by U's by using these CR equations. So we get VR and V theta, and now using 2 and 5, we get RUR. Since you can see that multiply this equation by R, we get V theta. So RUR is equal to V theta, and multiply this equation by minus R. Um, we get equal to u theta. So minus RVR is equal to u theta at z naught. So these are the polar form of Cauchy-Riemann equations. Uh, sorry. So we have derived the polar form of Cauchy-Riemann equations. So now we can also prove that the converse also holds. If we suppose these CR equations in polar form does hold, then we can also prove um, by using um, an alternative form of chain rule, we can also prove that the CR equations in Cartesian coordinates also hold. We are given giving the proof of that converse part in the end. Now we are going to prove the main part of the theorem which was remaining, that is f prime of z naught's representation in polar coordinates. Since f of z was ur theta plus iota vr theta and z was r e iota theta, we start with the Cartesian form of definition of f prime of z, which is ux plus iota vx. Since x is r cos theta and y is r sin theta, so ux equal to, um, as before, we can use the ux and vx, which are cos theta ur minus sin theta by r u theta, and vx is this. We substitute these values in this using the chain rule. So f prime of z now becomes like this, and we use the polar CR equation, since we have proved recently that the polar form of CR equations hold like this. So using these equations, in this equation we get ur plus iota vr is equal to 1 over r v theta minus iota u theta, which is on simplification becomes that. So we substitute back in this equation and it becomes as this. So here this is shown by the Euler's formula as e raised to power minus iota theta, and we replace this with e raised to power minus iota theta in the equation here. So we come up with the uh, polar representation of f prime of z, which is ur plus iota vr into e raised to power minus iota theta. And one thing that was a little uh, this was the thing that needs some more explanation. We are using the an alternative form of chain rule here. Um, Before that, we have used UR and VR. The chain rule for UR and VR and U theta and V theta. Now we are going from X to theta. So UX and VX, the chain rule, then an alternative form of chain rule is being used here. So this is the final result, and I've also explained the reverse part, that is driving Cartesian CR equations from the polar form of CR equations. Here in this one page, the steps are explained. You can check them. First step is take the polar CR equations. This is appearing to be blurry. First step is take the polar CR equations, apply chain rule from polar to Cartesian one, right? From u theta and ur, we are going to um, ux and uy and vx and vy. So over here, we are going to substitute these polar CR equations. So um, we get ux. This form is for ux, and this is for vy, and for uy this, and for vx this. So from here we get one CR equation, and from here we get the other CR equation. So we have proved here, shortly, we have given the steps that we can also start from polar CR equations and derive the Cartesian form of CR equations. So we can say that polar CR equations are equivalent to the Cartesian CR equations, or they are the alternatives of each other. Thank you very much. This was all about today's lecture.